this one had not set, so actually it causes to crack or something. Okay, so you want this whole thing to be one monolithic structure all the way. Okay, so then there is something known as a grout wall, by grouting or jet grouting the soil, and this is an example of a grout wall. I mean, it's picture you can see. You got a drill rod that goes in here, compaction and grout that is cased here, and then as you pull the casing out, you put this grout at the bottom. It's basically put this, you begin pumping through this here, and it comes out to the bottom here, and then you pull out the casing, and as you pull out the casing, you will get this grout to set, and you can see how it comes out eventually. Okay. Then there is also known as sheet piling. Remember, the objective of all of this is this vertical barriers. Sheet piling. Sheet piling is basically a steel or a vertical sheet pile. It's just push a sheet pile, a plate to prevent the contaminant to go. That's a very, in that sense, that if this is your contaminated site, you put a pipe, a plate here, and so on, and try to cover and go right down to the. So this is something about liners. We'll just ignore that. Actually, liners. This is how a liner is built. As you can see, you have a compacted. This is a geomembrane. These geomembranes are very okay. These geomembranes are very low permeability membranes. Okay. Yeah, this is a picture of a liner. Okay, so this is a landfill liner. Have you guys taken a course in landfills, or I asked that before? I don't think you have, right? So this is how it would look like. You got a layer of this is the base of what you defined was a dump. It's the base of an engineered dump. Okay, so you got a 2-3 feet of compacted clay. Okay, follow this diagram here. A few feet of compacted clay. On top of it is a 60 mil HDP liner, high density polyethylene liner. This is plastic material. Okay, it's not plastic, but it is similar material. Okay, this blue thing here. On top of that is what is known as a geonet. Okay, on top of that is a geotextile, and basically this is a drainage layer. And then you have rocks. You have a pipe here. The pipe is actually used to carry the water out, and then top geotextile and the top, sand and the top, and then fill. All right. The reason you want this leachate collection system here is you don't want water to build up. So the real protection comes from these two, the HDP liner and the clay. So all this liquid that is generated in a landfill called leachate, you don't want that to build up here, because it builds up slowly, it will make its way down. And for that you need this leachate collection system and geotextile, and the geotextile prevents sand and other things from anything from clogging this area here. So that's why you have this geotextile here in the top and the bottom to prevent clogging of this gravel here. The gravel supports this leachate collection pipe here, and that's the base. That's how the base of a landfill is prepared. Okay, you have, so on below the landfill waste, you have a pipe which carries the leachate away, so there is no water buildup, and because and below that is your layer, the two layers that provide protection to the ground below the landfill. Okay, and one of them is an HDPE liner, and the other is a compacted. All right, so soil bentonite barriers are usually the most common ones. It's a slurry of 1 to 5% bentonite with water. Gives a hydraulic conductivity less than 10 to the power minus 7 centimeters per second. When you design a landfill liner, that's usually the rule of thumb people use, 10 to the power minus 7 centimeters per second of hydraulic conductivity. Okay. The slurry supports the sides of the trench. We talked about that. Soil excavated from the trench is used to backfill the trench. Design considerations for soil bentonite barriers. You want to make sure the side grade is not steep, because it will not set, it will just run down, and then you will not have, so you have to have very flat terrain. It should be accessible because these are wide. Okay. You want to make sure the trench is stable. The slurry should prevent cave-in, so it is, it's a meter thick. So you take the stuff out, and you don't want it to cave in as the person. The other thing is contaminants compatibility. This is important. Bentonite is has got sodium cations. Okay, and those cations are sitting in between the silica and in between the clay platelets. Okay, once you have a chemical that reacts with bentonite, with the sodium, and exchanges it out or whatever, then you have a situation where the integrity of the bentonitic liner will get compromised, and it is not inert. It is a reactive material. Are you with me on that? Okay, so bentonite is this clay minerals, the silica and alumina, with sodium cations in the middle. That's sodium bentonite. Okay, if you exchange the sodium cation and put calcium or magnesium, the properties change. Now, if you have water or liquid that is a different composition, it will actually cause the sodium to be exchanged with, let's say, whatever is present, calcium or chromium or whatever, right? Now you have a different clay structure, clay the property there. It's still bentonite, but it's different clay. So calcium bentonite behaves very differently than, let's say, sodium bentonite. So you may have a situation where the integrity of the cutoff wall is compromised. Okay, because of the reactive nature of the bentonite that's present there. You want to make sure that the contaminant the contaminated site that you have, and if you are planning to put a cutoff wall which has bentonite in it, that there is enough that this one, whatever is present, does not actually react with that. Okay, as well as if there is water flowing from the side, if there is water flowing along the side, once the water comes in contact with the bentonite around the edges, it does not actually compromise the bentonite's integrity as a low permeable barrier. And it can be interfaced with other technologies, of course. So this is the preparation of a soupy mixture, as you can see, and then you put it in and compact it. Cement bentonite barriers are composed of water, cement and bentonite. Is not used for contaminant where you need a very low permeability, because again cement and bentonite will react and it will not get the low permeability that you want from bentonite alone. Okay, when compared with soil bentonite, it has a higher permeability and a higher shear strength. So for example, if you have a grade or something, or if there's any need for shear strength, this is the something to look at. Can be constructed at steeper slopes. Does not require a large working area because it's not that wide and it's homogeneous. This is an example of a cement bentonite mixture. You can see the cement being mixed and poured here, and this is how it will look like. Okay, it's pretty clear what it looked like, and you go as you go on. Then there is something known as a treatment wall. So these are basically preventative walls. These walls will prevent the migration. Something known as a treatment wall. A treatment wall is a slurry trench wall used to direct the contaminant wall through a treatment zone. Remember I talked about funnel and gate my couple of days ago. A funnel and gate is an example of where you actually try to channel it. Remember, if you want to treat the water that's coming here, you may choose to put a barrier. So let's say this is my contaminated site, okay, but I know the groundwater is flowing in this direction. Okay, how do I treat the groundwater? Well, I am thinking maybe I can put a wall here like that and another wall here like this. Okay, so what will happen, all the water will start to flow through this zone here, and you can make it narrower. You can go further here and further here, and you can make it narrower, right? Now the water has to go through here, correct? And you can cut and you can make a place to treat. All right, so that's slurry trench cutoff wall. The other way you can do is you can actually put something in the treatment itself, right? For example, let's say you have this one. Okay, now you want to put cut a wall like this thing like that and put something in here that provides treatment. Okay, let's say zero valent ion, for example, for precipitation, or we talked about in soil vapor extraction, we talked about horizontal trench sparging, right? So that's a treatment system. It's also a wall in a way, but it's a treatment system. So whatever comes here is a lot cleaner. Okay. So when you guys, some of you guys are doing contaminant transport models, right? This is something to think about. That if you, so the purpose of a model is to develop the model, but you can look at, okay, if I put a treatment around it, how will my plume shrink? How will my plume change? Right? The beauty of a model is that you can play it on a computer system and see different scenarios without actually trying it on the field. Okay? If you are doing a computer simulation of a contaminant transport model for a particular site, it might be worth your time to see what treatment I can do so that my plume can shrink by putting different scenarios around it. Okay? But the amount of time you spent in developing a flow model, a transport model, and calibrate the model and verify the model and all that, it's not a whole lot more time to see, okay, how can I treat it? Right? So just something I want to throw it out there that you should, if you are modeling, is a part of your thesis, that's where that's a lot of value that that you can add by saying, okay, if you put a treatment system here in this format, the plume is going to shrink in 3 years. If you put this one, it might shrink in 2 years, and different scenarios, different concentration, different amount, and it's all a simulation, so you don't have to spend money or anything trying out actual field results. So slurry trench walls, coming back to what we are talking about, used to direct the contaminated groundwater through a treatment zone. Groundwater is degraded, precipitated, absorbed while passing through the treatment area and can operate for years without maintenance. Okay, this is an example of waste material. You got a cap on the top and you got a porous media. The porous media is used for treatment. The water is flowing in this direction from left to right, and then you will find that water that comes out here will be treated. So it's not just for confining. This is an example of this was a neat little there was a let me see if I have it. So this is a computer simulation that I thought you can enjoy, but but it is showing as a JPEG. Let me see if I can run it on a. This is a simulation which shows. Okay. Anyway, I don't want to waste time on this. Let me go back here. So this is an example of. This is actually a simulation which I can't run right now. I don't think I have all the details. But anyway, you've got a slurry wall here, you've got a reactive wall here, a sheet pile here, and the plume is coming here. You can see the plume is going through, being forced by the sheet pile and the slurry wall to go through this, and that's where the reactive wall is. You can see that, right? So this is a cap. What I talked to you earlier was a liner. So this is a cap. Cap means the top. You got a vegetative layer here, which for the top soil. Below that, you have a protection layer for the top soil because you don't want things to migrate up. You have a granular layer, which is which provides drainage, as you can see here. And then below that is the geomembrane, and then the waste here. So waste, a gas collection layer, a geomembrane. So basically you want to make sure that there is no water buildup on the. So you have your waste, you cover it with a layer of geomembrane, which is very which provides the moisture from coming inside the waste, and then you provide a layer of a drainage layer on the top, and then the top layer. Okay, pretty much that's it. This is another one of the same kind, which talks about the bottom and the top, the bottom layer and the top layer. It's otherwise it's nothing. Okay, so that is the different treatment mechanisms. Okay, that is not exhaustive. There's a bunch of other treatment mechanisms that are used as well. We don't have time here to go through all that. There's electrokinetic remediation, there is steam-based remediation, there are some other remediations as well. But these are by and large the larger, more applied, the ones that are more applied. Okay, it gives you a good starting point to develop newer techniques. Remember, every single thing you can customize to your site, and you should look at some level of customization. You know, for example, if you are doing thermal desorption, okay, you're doing desorption for this particular, but what about the others? If you have metals along with hydrocarbons, if you have this along with that, how do you do it? If you have moisture along with it, how do you treat the water? Okay, so a certain level of customization, as well as your own acumen and your experience and your ability to break down the problem is necessary. This is what you learn here is the tools. These are the different techniques that are out there, but you need a solution that is cost effective, that works for your case. And remember, the geology of every single site is different from every other site. Geology is different, soil characteristic is different, everything is different. So some may work better, some may work not as good. You never have one size fits all. In some places soil vapor extraction is great, some places maybe you have to use chemical oxidation, maybe you have to use multiple techniques at a particular location. All right, so I gave you here a wide variety of different types of treatment technologies that you can think and use. You may have to build on those. You can try some of them as well, but it's possible, like fly ash and cement. You know, you can different ratios of fly ash and cement, right? So with that, I will move on to if you have any. Do you have any questions on this? No? You don't have any questions on this? So then I'm going to move on to site risk assessment. Okay. So in risk assessment, there are 4 major things to consider. There is a hazard analysis and exposure analysis. Sorry, hazard analysis, exposure assessment, toxicity assessment, and risk characterization. These are the 4 broad things you need to think about. So we talked about the example of having a drum in the corner of the room. If it is present, there is a hazard that's present, right? But exposure wise, if the drum is exposed, we are all sitting here, we have a pathway. It's coming through the air. If it contains volatiles, it's coming through the air, we are possibly breathing it. So source, pathway, receptor. Those are the 3 things that are needed for risk to manifest itself. Okay, what are the 3 things that are needed for risk to manifest itself? No, let's go with that. Again, source, receptor. If you intervene in any one of them, your risk drops. Okay, you take the source out, you can have the receptor and the pathway, there is no, or you can take the pathway out, or you can take the receptor out. Okay, so that's the first. Now in the risk assessment, there are 4 steps. Hazard analysis, identifying the hazard, the chemical of concern. If that barrel contains just water, there is no hazard, right? If the barrel contains gasoline, well, there is a hazard, okay, or diesel. Exposure assessment, identifying contaminant releases and exposed population. Okay, going by our simple example, we are the exposed population. Okay, anybody else who comes here has an exposure, and when you do a risk assessment, you have to think beyond just a few people who are sitting here. You'll have to look at maybe children might come here, maybe who else institution allows to come. So you have to look at all that. So, and we'll talk about that in a bit here. Potential pathways, right? Let's say groundwater is contaminated, right? So groundwater, and it comes to my well, drinking water well. Now I take the water, I drink the water, I'm ingesting it. It's also coming because I take the water, put it there, I breathe. I take a shower for 10-15 minutes using that water, it's in the room. It's going to be in my room. So I inhale it. I take a shower, it comes in through my skin contact. Different pathways. Okay? You have to find the exposure and concentration for different pathways. How much am I getting exposed to in different pathways? I take a shower of 15 minutes. Okay, in 15 minutes, how much exposure do I get? Okay, if I have a child in my house, how much the exposure will the child have? The child taking a bath, another 15 minutes, right? So all that, you have to make sure that you have to identify the subpopulation that is most sensitive and identify the risk for it, because you want to be on the conservative side. You want to make sure that the population that is most vulnerable is the one that is protected, because the risk for that particular population is highest, and if the risk is highest, you need to identify that. The others, the risks are lower, but if you protect that subpopulation, then you'll protect everybody else. Okay, so that has to be kept in mind. I'll come back to that in a bit here. And you need to think about contaminant uptake from each pathway. You need to do a toxicity assessment, and then risk characterization, which is cancer risk versus non-cancer risk, and then uncertainty around the whole thing. The uncertainty is a very important aspect of risk assessment. Okay, if for example, if you ask me, risk assessment is a very, you can do the process, and we'll talk about the process, and hopefully by the end of it, you'll have a reasonably clear idea of how to do the risk assessment. The problem starts to happen because there is a whole bunch of other things that start to play a role. For example, voluntary risk by versus involuntary risk. Things like perceived risk versus actual risk. So when you go and tell somebody that your risk of drinking this water is 1 in 100,000, people's idea is that I don't want to be that 1 in 100,000. Nobody wants to be that, right? So they think it's very risky. Whereas anywhere from 1 in 100,000 and lower is very low risk. They do a lot of things on a daily basis that is much more riskier than that. Driving a car, crossing a road, all those things, much higher risk than that. But that is a risk they have taken. When I sit behind the wheel of a car, I have assumed the risk that I might die of car accident or I get injured. It's a risk I have taken as a price for the convenience of getting to my place in time. But when you tell somebody that you drink this water, it is not a risk that they are willing to take. They are not. Why should they? So you see the difference? Perceived risk versus voluntary risk versus involuntary risk. Again, perceived risk versus the actual risk. Okay, you see those terms? You know. So involuntary risk is. Let's give you an example. Let's say if they tell you, like sitting in a taxi and driving your own car. If you drive your own car and if you get into you take that risk. But if you're sitting in a taxi, you want a higher level of safety, right? You expect the driver, because you are not taking the risk, that person has to make sure that you're not exposed to that kind of risk. So it is not only just the computation of risk, but it is how you communicate the risk, how you interpret the risk and communicate the risk, that plays a significant role as well. So there are people who are risk communicators, who can talk better than you and me. You and me are people with an engineering and science background. We get caught in the numbers, 10 to the minus 5, 30,000, 50,000, 1 in 50,000, 1 in 100, 1 in 100,000. We get quickly caught in the numerics. Whereas at that time, you need somebody to explain in a different way sometimes. So there is a whole area of risk communication. Okay, we are not going there. Okay, if you are doing risk assessment, if you're planning to do risk assessment, keep those things in mind, that you might be good at doing the assessment, but maybe for communication, think about someone else, somebody who knows how to communicate. Okay, I just wanted to leave it out there. Anyway, that's not our area, that's not what we are talking about. We don't want to get into that. So, linear low dose cancer risk is given by the CDI, a chronic daily intake averaged over 70 years in milligrams per kilogram per day, multiplied by a slope factor. So there are a few documents that I can pass it on to you, that you should have it as manuals. They're available on the net. We can take a look at it. They give this data. So SF is a slope factor. What is SF? It is the upper bound probability of an individual developing cancer as a result of lifetime exposure to a particular carcinogen at a particular concentration. Okay. So CDI for benzene in drinking water is 0.0025. The slope factor for benzene is 0.029. If a person takes 2.5 parts per million of benzene, if a person has a chronic daily intake of 0.0025 milligrams per kilogram body weight per day, then the risk is 7 times 10 to the power minus 5. Is it clear? So this is all, we are just talking about cancer risk. So cancer risk is lifetime consumption. Okay, for an adult, if you're just considering cancer risk for adults, is 56 years, because first 20 years is not considered. So, but it says averaged over 70 years, the chronic daily intake, how much are you taking every single day, multiplied by a slope factor. The slope factor is the upper bound probability of an individual developing cancer as a result of lifetime exposure. Okay, so you multiply the two and you get your risk. Is that clear to everyone? Is that clear to everyone? Okay, so that's your low dose. In high dose, the equation changes. So let's not worry about the change of the equation. Let's look at the process of risk assessment itself. Okay, the equation changes. Here the risk is 1 minus exponential of minus CDI times CF, okay, as opposed to just CDI times CF. Okay, let's look at, so that is cancer. We'll come back and revisit it. Okay, let's look at non-cancer. Non-cancer, you have what is known as a hazard quotient. Exposure divided by a reference dose. Now, there is a difference between cancer and non-cancer. In cancer materials, sorry, in non-cancerous stuff, there is no, there is a dose below which nothing would happen. It's called the reference dose. Okay, below that nothing will happen. In cancer, there is nothing like that. There is no lower, below this, if you drink benzene, nothing will happen. Okay, it's basically all risk on all this. But since you cannot have zero, you have to have a number there. You see what I'm saying? In non-cancer materials, you have a threshold. Below the threshold, nothing is known to happen. That is the reference dose here. So in non-cancer, instead of, so we use a hazard quotient. Exposure divided by that reference dose. Okay, it is not expressed as a probability. Okay, you compare exposure level to a reference dose. Reference dose is the level of exposure below which it's unlikely to have an adverse health effect. Okay, so if I take this amount below this particular, I'm not expected to have any health effect. It's a reasonably conservative number. It's a table. You can look up a table for reference dose for certain things. Okay, so all we need is then to find out the exposure and the RFD for the same duration. For chronic, it's 7 years to a lifetime. For subchronic, 2 weeks to 7 years, and short term is 2 weeks. So all we are saying is, whatever exposure period is happening, make sure you consider the same reference dose for that period. All right. So if you have, for example, so reference dose when you are exposed for 2 weeks will be different from reference dose if you are exposed for 5 years. Are you with me on that? So that's why you have acute, subchronic, and chronic. So you take the same exposure period that happens, divided by the reference dose for that period, and you get a hazard quotient. If that hazard quotient is less than 0.2, that means you are 20% of the reference dose. You can consider that the risk is negligible. With me? What happens if the exposure is at reference dose? Exposure and reference dose are same. Hazard quotient is 1, which means borderline. Okay, hazard quotient, sorry, a reference dose, you are touching the reference dose means unlikely something will happen, but you are getting there where you might have something happening. Because if you exceed it, there is an expectation that something will happen. Definitely 20% is a cutoff. If you're less than 0.2, So hazard quotient is exposure divided by RFD, reference dose. If this is less than or equal to 0.2, that means your exposure is less than or equal to 0.2 times reference dose. A reference dose is when you have there's unlikely and it will have an adverse effect, and you are even 0.2 of that, which means you can be reasonably confident it's not going to harm you. A very different concept compared to cancer causing material, which is where you are talking about just risk as a probability, right? So aggregate risk of multiple substances is summation of risk. Okay, so and same thing about on the both cancer side and on the hazard index and on the risk side. Okay, if the exposure happens over multiple pathways, okay, then the total exposure is the sum of all pathways. Now, if you want to, so exposure, let's say dermal and all that, but even you have to look at the target. So, for example, let's say I drink something, it attacks my kidney. I drink something else that also attacks my kidney. Right? Now you see the risk of me developing kidney problems from those two sources perceived to be independent but both attacking the same organ will be a lot higher. So you need to add them. Okay? So the risk is higher. So that's the total exposure cancer risk is risk by different exposure pathways, and hazard indices are calculated separately for chronic, subchronic and shorter term durations. Okay, risk assessment is not an exact science. Okay, different people may, while there is a protocol, there is a process, the numbers you might, especially in the uncertainty side of things, you will start to take some value. Some people will take a Gaussian distribution, some might take a triangular distribution, some people are more might take numbers which are more optimistic, some might take numbers that are more pessimistic, and they might all compound. So there is that issue with risk assessment as such. Okay, variation in results due to differing approaches, assumptions and use of toxicological information. Definition. So remember last time I was talking about you go to a journal, you read up what is the impact, get the null, and you take your null, and now that itself is a, somebody's done experiments with 5 rats and come up with certain low adverse effect. Somebody's done with 30 hamsters, get another lull versus null, all that. So even going there, it's difficult, right? Definition of acceptable cancer risk also varies. Some say 10 to the power minus 6, some places 10 to the power minus 5, whatever, right? Like, so acceptable hazard quotient might vary too. It is the ratio, less than 1, no adverse effect is expected, but the Health Canada document says 0.2 is where you can be reasonable that nothing will happen. Okay, so that in a high level is the risk assessment. Okay, now what I want to talk about is a preliminary quantitative risk assessment. It is a step towards a detailed risk assessment. Okay, the detailed risk assessment is when you do site specific information, you look at the people who are exposed, look at the people who all that, like specific information you feed into the system. Okay. For example, in a situation you say, okay, we attend classes for so many hours a week and so on, whereas PQRA is more generic. This is what you will need to, this is what you should learn to actually eventually do it's like a stepping stone. Okay, so let's go with that. It is not supposed to replace a site specific, which is much more detailed. SSRA is quite extensive compared to PQRA, and PQRA is limited to standard conservative assumptions. Background sources is not quantified in PQRA. So I want to find out that gasoline, what is the exposure to. but I'm also living in this city, and there might be a certain level of exposure that's happening to me outside that. That is considered in a site-specific risk assessment, but not considered in PQRA. Are you with me on that? So you might be doing things as a group, or we might be doing, which will either enhance the risk, right, or have an impact on the risk. So that's what it means by background sources. Okay, I'm going to get on with this. The PQRA process: screening and identification of contaminants, identification and description of potential receptors, and identification of exposure pathways we need to know. Okay, so screening and identification of contaminants of potential concern should be screened using guidelines for protection of human health. Applies 20% of TDI or RFD, right, hazard quotient. Preliminary remediation goal is also considered, and okay, let me just where am I? Here. So this is all sampling stuff. We have gone through it in our remediation, right? The sampling of contaminated media, soil, dust, drinking water. So you need that sample. If you want to, from breathing, you need to know how much is present in the water, right? So in the air. If you're drinking, how much is present in the water? Sampling protocol and all we have talked the previous days. Okay. Identification of potential receptors. Persons who visit the site. Infants, anyone from 0 to 6 months, any child or baby. Toddlers 7 months to 4 years, children 5 years to 11 years, teens 12 to 19, and adults over 20 years. Then construction workers, excavators at industrial sites. These are the potential receptors that you have. So this is how you formulate the problem. You have so what is the land use? So the site that you're trying to find the risk for, what is the land use? Is it a daycare? Is it a urban? Is it agricultural? It's what? So you tick whatever works for you. Then you go and see who are the receptors. Is it employees? Is it general public, toddlers and so on? Critical receptors. Okay. Infant, toddler, child, depending on who is this one here. Now this Canadian Native community is a separate box here, because they have a different diet and all that, and that needs to be factored in. Exposure pathways, ingestion, particular, take all of them. So for example, let's say you have general public, toddler and child, let's say, or whatever, then you select all the ones that. So this is how you start to formulate the problem. Okay. Use, exposure assessment and limitations are stated. Okay, let me come back here. So exposure duration and frequency assumptions. Okay. I'm going to do something else here. Okay, this is the one I will give you a copy of. Okay, because there are tables in this that I could not put it in my slides. So this is the table we just saw. Okay. So yeah, this is what I wanted to show you. So look at this. So look at this, recommended human receptors and their characteristics for PQRA. Can you read from there? No? Why? You forgot your glasses at home or what? How do I make it bigger? Zoom. Can you read now? Okay. We can make it even bigger if you. Okay. So let's look at this one here. Recommended human receptors and their characteristics. Okay. So age, if you're dealing with an infant, body weight is given to you. Okay. Soil ingestion rate 0.02 grams per day. Inhalation rate 2.1 meter cube per hour per day. Water ingestion rate 0.3 liters per day. Okay. Time spent outdoors, for teens and adults, I mean for children, that baby is nothing there. So skin surface area, hands, upper arms, lower legs, and so on. Okay. Soil loaded to exposed skin. You get all this data here, right? You get all this data here. You don't really need to find the data. The data is all given in the form of tables. Food ingestion, how much root vegetables did they eat? 83 grams per day. Other vegetables, fish, and for others. So this is for children, this is for teens, this is for adults, and construction workers. They are all more than 20 years of age. They don't have as much ingestion, but inhalation is a lot higher, and so on. Basically same as the adult. In skin is higher here because they're working on site. Are you with me on this? Yes or no? Okay, so you can see how useful this kind of a table is. Okay. Then the other table that you would need is this exposure duration frequency. That's also in that from that one, that manual. Hours per day. If it is an agricultural site, you can expect the person to be living on site. So 24 hours per day, 7 days a week, and 52 weeks per year. So it's pretty much round the clock exposure. Okay. If it is a commercial site, well, we all come here for 8 hours a day, 5 days a week, 52 weeks a year, and so on. Dermal exposure. And for life expectancy, we use 56 years from the age of 20 to 75 for adults. Okay. How are you guys doing? Is it good? Okay. So here I have put some of the equations here, which is also taken from that manual. So let's look at this equation here. Okay. What is the intake of a particular contaminant with soil ingestion? Dose in milligrams per day, milligrams per kilogram per day, is concentration of the contaminant in milligrams per kilogram multiplied by an ingestion rate. You saw that in the table there, right? Soil ingestion is 0.02, I think, for toddlers. Absorption rate from the GI tract, from the food tract. Okay. Days per week of exposed, weeks per week, weeks per year, and total year divided by body weight divided by the life expectancy for cancer risk. So you can use this to calculate the dose from soil ingestion, right? If I go here, the next one is dose from dust in the air. Okay, particulate concentrations, similar stuff. If you look at all these equations that I have here, they're all similar. Drinking water, all they're saying is what is the concentration present in drinking water, how much am I drinking as water, how much of it gets absorbed in it, and how long am I drinking, and what is my body weight. Average body weight for an adult is 70 kilograms, and life expectancy is 56 years for adults. Okay. So, and that's what you should consider. This is dermal contact. Again, area of skin that is exposed, dermal absorption factor, receptor water intake. Look at the format of the equation. They are all very, very similar. Okay. This is ingestion via food. Hey, what happened to my slides? Okay. What happened to my slide? Okay, my slides have ended. It should not. Um, you have more than this, right, on your slides? Your notes have a slightly different set, isn't it? Yeah, and I'm trying to find what happened to that. This is PowerPoint. Where is my okay, let's go Gyan India notes for student. Ah, this is the one. Yeah, sorry. This is same as what you saw, except that I made changes here. Okay, this is important. So are we clear up to the for the process now? So find out the dose, how much different pathways come, you add the different pathways, and then you determine the total estimated exposure divided by the tolerable daily intake. Okay, that will give you your hazard quotient. Okay, now I want to bring something different here. 747. Okay. I want to introduce you to something different here. So give me a. This is the same as others, but um, actually, if I can show you this, I can close the loop on this whole thing, and you would see what I'm trying to say here. Uh, but I can't seem to find it now. Let's see if I find. Okay, so there is chloride here. Behavior in water systems, exposure. This is what I wanted to show you. Okay, this is an example. So remember we were doing some. I want to tie this circle here. Remember we are talking about you work for a regulatory body and and your boss comes and tells you, okay, you find this, you find a particular contaminant in water, how you have to set up a tolerable, a maximum acceptable concentration. How do you go about doing it? Okay, so I want to give you an example so you know how that is done. In your risk, if you look at that equation, it's the exposure divided by tolerable daily intake. How do you find the tolerable daily intake? Okay, so look at this particular. I just pulled it out of the Health Canada website, but it says it basically goes and looks at literature. Somebody's done work on rats. Somebody's work on. I'm going to try and see if I can make it bigger. Let's see, where is Zoom here? Okay, so let's look at this. So look at how he's trying to make a case for the tolerable daily intake. Park your thought about risk. We'll come back to the risk in a minute. Just forget about that part. Let's look at how they calculate the tolerable daily intake. The effect of sodium chloride in drinking water on survival or pathology of albino rats were examined in a 2-year study, right? So they are basically doing a literature survey. Okay, the lifespan of the animal was not significantly impacted, and so on. And in a carcinogenic study, sodium chloride was administered to this particular genetically modified mice at different concentrations, and so on and so forth. And eventually, I did the Sprague dolly rats and drinking water. Eventually, they come up with some numbers. Okay, so the tolerable daily intake, and I'm going to just skip all of this because that's just immaterial at the moment, is, and I want to show you the equation which is important here. So if you look at this, he's talking about same thing, chloride. Okay, the low observed adverse effect level observed by Mobley et al. A development of 6 milligrams of chloride per body weight, and so on. Okay, based on that, he selects one, and this is what he comes up with, that the tolerable daily intake, this is an important equation. That's what he comes up with. There's sufficient, look at this, what he's writing here. There's sufficient data available to estimate a tolerable day based on 2-generation study where the no observed adverse effect level of 2.9 milligram body weight per day was identified. Okay, read that. So based on a whole bunch of literature, he has honed in on this one, on this particular study, and said this is an extensive study. The numbers lie in range with what others are saying. So I'm going to take 2.9 milligrams per liter of no observed adverse effect level, and you divide it by an uncertainty factor 100. Okay, and that is how he comes up with a tolerable daily intake of chloride is 0.029 milligrams per kilogram body weight. You take the LOL that everybody has been talking about, divided by an uncertainty factor. That can be 100, that can be 1,000, that can be, I think that can be whatever number you think, depending on interspecies variation, intraspecies variation, the effect that you are seeing, and so on. So based on all of this, you come up with what is known as a tolerable daily intake. Okay. Now coming back to my slide, estimated exposure divided by the tolerable daily intake is 0.2, or the reference dose for non-carcinogens. Okay. For cancer risk, it is multiplied with the cancer slope factor, and the ICLR 10 to the power minus 5 is negligible risk. Okay. Exposure to mixtures for non-carcinogens, The hazard quotients are summed for substances determined to have similar targets. So we talked about that. For carcinogens, so basically risk is additive. So risk from one path, risk from another path. If they are affecting the same target, they are additive. Okay. With that, I have come to the end of this. Do you have any questions? Any questions? I can give you this document, the Health Canada document. I can also give you another document I have from US EPA, an exposure assessment. Those are available online. You can get it yourself. I can give it to you. It's good to go through the process that they lay out. You've got lots of tables in it. You can look up the tables. You don't really need to do any, they will tell you how much of the skin is exposed, how much of the water a particular age group of person drinks, and so on. And then you can use those numbers. Okay. तो बंद कर दें? हो गया?